I'm Bob Hurst, back again with further information on setting up the TK76. This time we'll go through the procedure for setting up the color encoder. These two boards I'm holding, the luminance module here in my right hand and the chrominance module in my other hand, these two together make up the color encoder of the TK76. Before undertaking the encoder adjustment, make certain you have available the tools and equipment listed for this procedure in your manual. The gen-locking of the camera, though not absolutely required, does make the setup easier. As a general rule, any time a module must be removed from or reinserted in the camera, it's very advisable to turn power off while the board removal or insertion is taking place. To gain access to the color encoder adjustments, you must first remove the left cover plate from the camera. Once you've done this, set up the camera, waveform monitor, and vector scope as indicated in the sketch in your manual. If gen-lock is to be used, the gen-lock cable and sync source should be connected at this time also. And further, it's good practice to cap the lens while the encoder is being adjusted. Turn the bars switch to the on position and apply power to the camera. The positions of the other two switches don't matter for encoder adjustment. It's advisable, however, to leave them in their normal operating position, 0 dB sensitivity and automatic iris. At the power module, use an accurate meter to check the plus 12 volt supply. Since readjustment of this voltage makes it necessary to refocus and re-register the camera, you shouldn't alter the voltage unless it's below 11.6 volts or above 12.4. If the voltage is outside these limits, however, use the control marked plus 650 to pull the voltage to 12.0 volts. Make a note that the power supply voltage was altered to remind yourself to refer to the sections on registration and focus to completely realign the camera. Now, examine the color bar waveform on the waveform monitor. Note particularly the black portion to the right of the color bars themselves. To conserve power, the TK76 uses a modified color bar pattern wherein the familiar split field pattern is not used and a black reference is provided just to the right of the normal bar pattern. This right-hand black reference should be roughly as wide as a normal color bar. If it is this width, no adjustment is necessary. If it's too wide, as shown here, or too narrow, turn power off, place the sync module on an extender and turn power back on, and adjust C35 bars width to obtain the correct waveform, as shown here. Now turn the power off again, replace the sync module in its slot, and power up the camera again. Now, with the camera powered up again, re-inspect the color bar waveform. Here we have deliberately misadjusted the encoder to show the subcarrier that appears in the black bar for improper black balance setting. To restore correct black balance, adjust the I and Q black balance controls to minimize the subcarrier in the black. In a like manner, we can deliberately misadjust the encoder to show the effect of improper white balance setting. Here, unwanted subcarrier appears on white. To obtain correct white balance, adjust the I and Q white balance controls to minimize the subcarrier in white. Next, we must check the I and Q symmetry, also known as modulator video balance. To do this, first turn power off, remove the chroma module and place it on an extender and turn power back on. Then, connect a scope probe to test point TP5 as shown. Here, we have deliberately misadjusted the eye symmetry in order to show the effect on the waveform seen at the test point. The misadjustment allows baseband video to crosstalk into the eye chroma, pulling the subcarrier off axis. To correct this, readjust R108 eye symmetry, as shown here, to eliminate the crosstalk, producing a symmetrical eye chroma waveform. In a like manner, we connect the scope to test point TP4, where a deliberate misadjustment allows us to see a similar lack of symmetry in Q chroma. And a readjustment of R107 Q symmetry produces a symmetrical Q waveform. In the next steps, we shall assume that the camera is not genlocked. This means that the vector scope must be locked to camera burst. Since we're going to be setting quadrature, and since in this camera quadrature affects the phase of burst, any change in quadrature setting will change the reference we are using to determine the correct setting. As long as the corrections are small, we can arrive at the correct setting by 2 or 3 repetitions of the procedure. The errors will become smaller each time and will, by the 2nd or 3rd attempt, become negligible. If the camera is grossly misadjusted, however, the errors can become larger on each attempt. If you find yourself in this position, you must genlock the camera and run the vector scope from external subcarrier in order to reset quadrature. To reset quadrature, first locate R53 near the top of the chroma module. And with a clip lead having a very fine jaw, short the right end of R53 to ground. This removes the Q signal, leaving only I. The vector scope will show a single chroma phase with burst. This is I chroma and should be aligned with the I graticule. Using the vector scope phase control, align this vector so that it falls along the I-axis marking graticule of the vector scope. Now, remove the short from R53 and locate R56 at the very top of the board. Using the same clip lead, short the right end of R56 to ground. This removes the I signal, leaving only Q. Here we show the vector scope display that results. We have deliberately misadjusted quadrature somewhat to show that for this misadjustment, the Q vector misses the Q graticule marking. To obtain a correct setting of quadrature, adjust R34, quadrature, to cause the Q vector to fall over the Q graticule marks on the vector scope. If this procedure was done without genlocking, you must now go back and repeat at least once the entire procedure. Move the short from R56 back to R53, and looking at I on the vector scope, you will find that the quadrature readjustment has caused it to shift somewhat with respect to the I graticule marking. Readjust vector scope phase to make the I vector again fall on the graticule mark. Then reiterate the entire procedure until returning to the I vector shows that it did not move from its graticule marks. Then remove the shorting clip lead. Quadrature should now be correctly set. Now inspect the vector scope display carefully. If the dots representing the vector tips are all within their respective small boxes, then no further adjustments are needed to the subcarrier aspects of the signal. However, if Q gain is low, for example, then the magenta and green bars will be badly out of their boxes. Yellow and blue will be almost as badly affected, and the other 2 bars, red and cyan, will be only slightly disturbed. To correct this condition, adjust Q gain to put the bars into their boxes. Also, if I gain is low, red and cyan will be the most seriously affected, with correspondingly lesser effects on the other 4 colors. To correct this situation, adjust I gain. If the entire chroma signal is low, then an overall correction can be made with the chroma level control. Now, if these controls are grossly misadjusted, start by placing I gain and Q gain in their mid positions and adjust chroma level to put the bars approximately into their boxes. Then use I gain and Q gain as required to maneuver the bars into their boxes, remembering that I gain moves the vector tips in the I-axis direction with the strongest effect on vectors lying along or near the I-axis, and that Q gain moves the vector tips in the Q-axis direction with the strongest effect being on the vectors lying along or near the Q-axis direction. And if these adjustments don't suffice to get the proper vector scope display, it's quite possible that C13 chroma geometry needs correction. To set this control, it's essential that the vector scope be locked to camera burst so that you can see clearly the effects this control has on the signal. With the vector scope locked to burst, adjustment of C13 will be seen to offer a slight rotation of magenta and cyan, more or less independently of the other bars. Also, since C13 has a rather large effect on overall chroma amplitude, it will be necessary to readjust chroma level again once the proper angular location for the bars has been achieved. Once all controls have been optimized, the TK76 color encoder should produce accurately positioned bars. Properly positioning the bars does not, however, guarantee correct burst phase. If the camera has this Genlock cable connected and is Genlocked, and if the vector scope is referenced to external subcarrier, then you should phase the vector scope to put the bars in their boxes, letting burst fall where it may, and then adjust burst phase to pull the burst vector onto the burst axis graticule. However, if the vector scope is locked to camera burst, then you should adjust vector scope phase to put the burst on axis, which will pull the bars off as shown here, and then adjust burst phase as above to pull the bars to the correct location. Turning back to the waveform monitor, we may find that burst is the wrong amplitude. The burst gain control should be used to adjust the burst to 40 IRE units peak to peak. Similarly, the setup may be wrong. This may be corrected by adjusting black reference on the luminance module to obtain standard setup, 7 1/2 IRE units for most American operations. The white bar, or more accurately, the gray bar, should be at 77 IRE units. If it's incorrect, the luminance gain control should be used to pull it to the correct level. And sync level, which is adjusted by the sync level control, should be set to give -40 IRE units of sync amplitude. And that concludes our encoder setup procedure. Your TK76 should now be making virtually flawless bars and be ready to process properly the camera signal itself. I'm Bob Hurst for RCA Broadcast Systems. Thanks for your attention.